Welcome back, I'm Jeff of All Trades, and this is part 2 of the modding RollerCoaster Tycoon into a Peele horror film video. In part 2, we are going to talk about all of the code that we used to automate the mod that we created in part 1, or that we researched basically in part 1. And I did a little bit of a preview of this code during that first video, but this is going to be a deep dive. We'll go through all of the different files involved and all of the different operations that had to be done to turn this into a fully automated mod. Assuming you watched part 1, you're going to see a lot of the same concepts we ran through in the disassembler before revisited, so I'm not going to spend a whole lot of time talking about them. And assuming you didn't watch part 1 for whatever reason, I hope you enjoy watching this video in nightmare mode difficulty. Also, I just wanted to say I've been incredibly just blown away. I already gushed in the first video for like 5 minutes in the intro, so I'm not going to do that again. But just wanted to say the first part has been up for a couple days now, and I've just been blown away by the feedback. Thank you so much. So with that out of the way, this has been uploaded to GitHub already. Some of you may have seen it linked in the description of the part 1. And I've opened up every file in a particular order that we're going to be covering. I'm going to be bouncing around just a little bit, but for the most part, we'll be working from kind of the bottom most part of the project up to the very top, with the exception of the main runner, which only takes a few seconds to minutes to cover. So we'll cover that real quick. Then we'll cover some of the structs that we'll be using, kind of helper structs we'll be using, then the utility scripts, and then that'll be that. So with that said, let me close that portion of the window right there. And let me go ahead and blow this up. Let me see what it looks like. One more zoom level in. I think that's a little too much. I think this will be okay for now. I'm sure you all let me know. For this, I think it's going to look okay on your screen without being... Let me see what this looks like. You know what? We'll leave it like that. That's fine. So I've got a bunch of comments and license at the top. The license, by the way, I put it there just so no one copies this over without attribution, but it's an MIT license, so as usual, you can do whatever you want with this code. I don't really care. I just hope that you'll take the time to actually credit it back to the original author. So this is the main runner program. This is the RCT horror mod script we ran a few times in part 1. And this really serves some very simplistic functions. It basically just serves as the argument parser, and then depending on what commands are passed in, it'll run some of the imported functions from the utilities that we have there. So let's just start from the top. We'll work our way down. We'll do this with, like I said, each and every file. Some of the files are more technical than others. Some of them are only going to take a few seconds to walk through probably. Others will take a lot more just because of, I'm staring at this one that's up next. We're actually going to skip that one for now, but the bitmap one is going to take a little bit of time to explain, just because, as I alluded to in the last video, the system that RollerCoaster Tycoon uses for packing and loading bitmaps, specifically the compacted bitmaps, can be a little hard to understand. So we're going to take it slow and fully understand it. But for now, we're going to just quickly go through the runner program. Again, like I said, it's basically just an argument parser, and then it launches whatever utility script based on these arguments. With the arg parser, I've set up subparsers, which if you haven't worked with those, they allow you to do something like this, where I can run the script. If I run the tac h for help, it'll show you that the script has multiple commands. So we have bitmaps, dump, patch, and show. And of course the default help option here. What those subparsers allow me to do is, for example, the command to, actually let's use a more simple command, and I'll go ahead and run RCT here in the background, so we just have an instance running in the background, and we can use that as our kind of guinea pig here. All right, so we don't really need to see it for right now. We'll just let it run. Let's say if we wanted to do the show command, we'll run show. We can also use tac h with just a single command. Excuse me. This is a poor choice. Let's not use show. Let's use dump, because that actually has some arguments. There we go. So I can set up different sub arguments for each sub parser, so to speak. So for each command, I can have my own set of arguments. Dump's going to have its own set of arguments. Bitmaps is going to have a different set of arguments that it needs. Not nitmaps, you nitwit. It's bitmaps. There we go. So bitmaps has its own arguments, and then patch, of course, is going to have different arguments. So the subparsers kind of make that process a lot easier. Other than that, there's really not a whole lot to see here. I guess some things to call out while we're talking about the arguments for each mode here. So show doesn't really have arguments because all it does is dump the DIB and the palette from the current running process. Dump introduces those two as output paths, so you can specify which path you want to save your palette, which path you want to save your DIB. Bitmaps has quite a few because it needs the palette, the csg1.dat file, the csg1i.dat file, to fully read in all the bitmap data from the files, as well as a out directory. And we'll go ahead, we may run that one again. We may run these all again in the course of the video as we go through their particular files, just to show you, demonstrate again how each one of them runs. You'll see that by default, if you don't specify this argument and you just leave the out file blank, it's going to write to the local directory with rct_patched.exe. And that the intent of that was to make sure people weren't accidentally overwriting their original rct.exe, and instead it would just create a separate executable. However, you'll see I've added a note here that says you probably want to rename this to rct.exe, or just output it to a different directory altogether and just name it rct.exe. The reason for that is if you run the game with rct underscore, actually let me just go ahead and see if we can demonstrate this. Let me make a copy here in my project directory. I hate this on Windows 11. I'm sure there's an easier way that I just don't feel like making the keyboard shortcut for the renaming. Oh, I do have to close my... Oh god, I forgot to turn on my volume. That was a lot of circus music to my eardrum. All right, there we go. So if you have the executable called something else, you'll run into weird little things as you're playing. So like when you go to load a saved game, you're going to see the folder is empty, even though, let me pull this up in another window here. If I pull up this directory, actually it's not going to show them. It's going to show this 001 file. The reason for this is, to be honest, unclear to me. I'm sure it has something to do with the way RollerCoaster Tycoon has set up. I don't know if it's a protection thing or if it's just a weird data input thing with the original executable. But your game has to be called rct.exe in order to load those saved games. So actually, instead of running the original one, sorry, I had to cut away because my Gmail came up, and Lord knows I love all of you, but the people who watch my videos, I know what you do. The majority of you do for employment, and I'm not about to dox myself to you lot. I don't need any help doing that. Anyway, so instead of running the original one, I'm going to run the patch version, which I've put in a separate directory and renamed to rct.exe. And you'll see those saved games come up again. Again, I didn't spend a whole lot of time, deep diving and reversing that aspect of the executable. There's probably a good reason for it. All I know is that you probably don't want to leave your output or your patch program named something other than rct.exe because you might run into little issues like that. All right, with that said, the only other two arguments here are just if you want to replace the default offset we use for the bitmap for the explosion animation. So we use the skelly, as I colloquially call it, lovingly call it in our first part, that skull animation or bitmap. And then you can also select a WAV file to play instead of the default one I've used of css25.dat, which is that horror track, in case you want to play whatever you want when the explosion happens and the applause happens. So yeah, other than the argument parsing functionality of this runner program, the only other thing is our main section down here. We just set up a logger to do some logging messages as we go along. And you'll notice if you looked at the GitHub when the first part of the video was released, I don't know why I had these as lambdas before. They're now just functions. I don't know why I overcomplicated that. Regardless, all the rest of the main program does is parse the arguments and then pass them into a command based on what flag was sent in from the user. So for example, the user specifies the bitmaps command. It's going to call bitmap extract from this file, which we'll go over in a little bit, and pass in the arguments that we parsed from the user. And if anything happens in any of these sub scripts, we'll catch the exceptions here and log them. Also, I've become aware, at least through a few people, that apparently this is not Pythonic. Apparently some people in the Python world hate using dictionaries as kind of like a switch for functions. I'm sorry if this is you. I think it suits this purpose really well, so I just did it. I'm sorry, I did it. So yeah, I've updated that. I've updated actually a few things as I've gone through and prepped for the second part of the video in the GitHub repo, which I'll push those changes sometime after I record this tonight. And of course, if you find anything else that looks off, I already did get one note about the requirements file being off when I first uploaded it, so thank you for that. And if you have any suggestions or feedback, or if something's broken, please feel free to put a merge request or an issue in the repo. So with that out of the way, let's close the runner program. That one's done. Like I said, we're going to skip bitmap and come back to it after we get to the other structs that are located in this subdir right here. So these struct classes that I built here, they're mainly just, sorry if you heard a blip there, I just closed the RCT window in the other monitor and it made a little sound. These are mostly just helper structs that are very simple. They take the sort of windows. In fact, let me back off this guy here so we can see this. They take the structs we talked about that are defined, in the Windows documentation and the Windows libraries, like this guy right here, which is from, you'll remember, if I can pull the window over. Hello. There we go. You remember this guy from part 1, BITMAPINFOHEADER, our good friend who helped us figure out a bunch of metadata about the main DIB that's painted a screen, and had our color table right after it in the bitmap info structure here. So in Python, you'll notice I've used a feature called a decorator with this. It's preceded by the @ symbol or the asperand, not to be confused with an ampersand. And I, to be frank, have not used data classes a whole lot in my other projects for work, etc. But once I was turned on to them by a fellow developer, I really like the concept, and in this case they worked really well for just one feature. I'm sure there's a bunch of other features that are extremely useful that I'm not going to hit on here. So the feature I liked about these is instead of making a constructor like this, which is typically what you'll do in Python, you have, you pass in your parameters to the constructor here, and then you end up doing something like, if you're not doing any operations on these values up here, you basically just start assigning them into the object of the class using self. So self.name equals name, self.unitprice equals unitprice, blah, 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 blah. And that's really all I wanted my constructor to do here, is just take in all of this data as argument in this data structure right here, and then just assign it to self. And so this data class decorator basically does the same thing as if I wrote this as a traditional constructor like bi size and then bi width, etc., etc. And then I went down here and did self.bi size equals bi size, self.bi width equals bi width, because I'm not changing the values or doing any manipulation on any of them. I literally am just taking them in and assigning it to an object so I can read them back later. And so the data class takes care of that for you. All you have to do is specify the type of each parameter that's being passed in. I've also got a couple of constants here that we'll use later on, and I'll talk about what these format strings mean and the size and everything at that time. So because we really just need to generate an object of this class whenever we want to use it, there's really no other operations that it has. It just takes in data from raw binary and generates this struct in Python. I've used a sort of like a factory method here called generate. It's denoted with another decorator called class method, so that I get a instance of the class here. I don't know if that's the right word if I want to say instance of the class. But basically, let me put it this way, so I don't offend any of the Pythonic people who are screaming at me through their screen right now. What this generate function is going to do, it's going to take in the class itself and some data, and that data is just all of this stuff passed in a list or a tuple, basically. This asterisk, if you haven't used that in Python, will basically unpack that list, and it basically just assigns out all the data in a row to all these separate class members that I've specified here. So what I would end up passing in would be something like, and we'll see this later on, but just to give you an idea, generate, and then I might pass in a bunch of binary data in a tuple like, I don't know. You wouldn't see it directly because we're going to read it from a process, but let's say we just were reading raw bytes. We'd have something like the size. I don't know what you would put there. And then we'd have like, or I guess it would be an int. There we go. And it would be 0x40 in Python. There we go. Size, and then you can do width, and I'm just making up stuff here. Height, planes, you know, et cetera, et cetera. And so when you do that asterisk operator right there, it's going to unpack these in order and basically going to assign them in order down from top to bottom of this list right here. Hopefully that makes sense, and hopefully I explained it in a high enough way and a low enough way that I haven't offended any of the Python people, but I've also gotten the point across to people who may not have worked with these kind of patterns before. So that kind of pattern you see in bitmap info header is going to be repeated in the next couple structs here with like RGBQUAD. Again, this is right from part 1, this guy right here. One thing that is a little bit different about the RGBQUAD is I've added a helper function here called as tuple. And the reason for that is when we read in the binary data, we're going to read in blue, green, red, and reserved in that order, just like you know, in the regular Windows struct that we're using here. When I return it back, I wanted to have all of the values in the RGB order. So as tuple, I did it again. I feel like I did that in the first video as well. As tuple will return the same values from the object in RGB order. There's also one little wrinkle down here in the generate function that's a little bit different. And that is if we only receive a blue, green, and red value, we automatically add a 0. And because we're taking one tuple and appending another tuple or joining them, you have to pass it kind of like this. So basically all this is doing is if I only get, you know, blue value of 0xff, 0x00, let's say we just get pure blue or something. If I only get the BG and R values, I'm going to go ahead and add a tuple like this, and that'll give me a full 4-value tuple of that. And that's just to make sure that if the user doesn't specify the reserved, that it gets set. Because remember, this is always, always, always going to be 0. So that's all that is. Pretty easy. Hopefully so. So far, so good. So let me go ahead and save. Actually, let me go ahead and undo all my changes because I'm too afraid that I've messed something else up when I did that. And yeah, that's about that for RGBQuad. The next one is TGraphicRecord, which if you remember, this one is not a Windows struct. This is right from the RCT Technical Information Depot, the page we talked about that pretty much saved the video, where James and Henry Winklestein, James Hughes and Henry Winklestein discuss how bitmaps are loaded from CSG1.dat using the indices in CSG1i.dat. I still struggle with making sure I enunciate the right CSG files there. So we're going to come back to this when we go through the bitmap in just a moment. But that TGraphicRecord struct I'm using in Python is basically this guy right here. We have, let's see if I can do a quick side-by-side. We have a start address, a width, a height, an X offset, a Y offset, a flags, and then we have an unused bit for padding at the end there. Again, there's a small little wrinkle compared to the other structs for the TGraphicRecord struct. And with the data class, it has some helpful helper functions like post init so that you can do some operations after the object has been initialized. And so I utilize that to do a quick check to, or not even check, but an operation to ensure that whatever we get passed in for flags, we only take the lower 4 bits because as you'll see here, only the lowest nibble is significant. So the upper bits are masked out. And if you are not familiar with how that math works in binary math. Let me see if I can get my calculator a little smaller. I think it's suffered from when I moved from my smaller monitor to this one. There we go. If I have a flag value, for example, of let's say 8, 5, for my purposes, or for RCT's purposes really, we only need these lower 4 bits here. And so we AND this value with F, like so. That will give us an ANDed value with 4 ones, which masks out the upper bit of 8 and just gives us 5. So when we go through, in fact, let me see if I have an example here in CSG1i.dat where the flag is different. I don't think when I looked through there actually were too many examples, if any, where the flag actually had that upper bit set. But let me see real quick. I'm just browsing through. Okay, yeah, actually there are a couple here I see. So like in this row here, if we look at the breakdown of this TGraphicRecord, if you remember, each row here is one TGraphicRecord. First 4 bytes here are the start address. Then we have 2 bytes of width, 2 bytes of height. What is that? 2 bytes of the X offset and Y offset each. And then 2 bytes for the flag, and then 2 bytes for the padding, basically. Now you'll notice that the flag is hex 11. But that's not a valid flag. There's only, what is it, 1 for a direct bitmap, 5 for a compact bitmap, and 8 for a palette entry. So when we take the value of hex 11 and AND it with F, we get just 1, which gives us the more accurate flag. So that's all that little post-init function is doing. Otherwise, it functions just like all the other structs we've seen so far. All right, now we'll tackle the beast that is bitmap.py. And believe it or not, this will probably be the most complex file of the mod, simply because it takes a little bit more brain work to fully grasp what's going on with the different bitmap formats that RCT uses. And you'll see I've got some unpushed changes here because I also did some refactoring as I was making this video to just move the constants into this class. It didn't make much sense to have them just floating out there, so I moved them back in. Those constants that you see right here are the 3 types of flags. Again, 1 for direct bitmap, 5 for compact, and then 8 for a palette bitmap. And then this mode is going to be used later on when we actually write the images to disk as files. We'll use RGB mode of the image library. And then we have all the data that we need to actually make the bitmap, including the width, the height, and the data, which you'll see is a list of tuples of ints. So what that means is these are actually RGB quads as tuples. So when I have my bitmap data, it's going to look something like, you know, you could do something like RGBQUAD. Let's see, 0xFF00.as tuple. And that's going to return it. Remember, as tuple is going to return it as RGB, whereas I passed in the values as BGR, and so that ends up being, you know, 0xFF, and then so on. Obviously, there's going to be more than one RGB quad. Actually, in some of them, there actually is just one, a single pixel, but you get the idea. We're going to have a list of tuples that represent the RGB values. That's what the data is. And then a file name, which we're going to use obviously to write the file. And as I said, when I made this, and you can change it if you want to, I made all the file names both the decimal and the hex address of where these are located in CSG1.dat, so that I could easily find them in both files and know exactly where they came from, and also so they're in order, the order that they're listed in CSG1i.dat. That will forever plague me. All right, so let's get to these different bitmap types that we have here. So first of all, there's a generic generate function that's called, and it does not care what kind of bitmap is being passed in. It just needs the TGraphicRecord, the color palette to use, and then the color table data, which we're going to obviously grab from CSG1.dat. So whatever flag that it reads from this TGraphicRecord, it's going to call a different function in return. and then just pass in all that same data to generate the right bitmap. So for example, if we get a flag for a direct bitmap, we're going to call bitmap.generateDirect, which is this next one right here. So let's go look at these. The direct bitmap is probably the easiest to wrap your head around. The palette one is pretty easy as well, but this one's probably the easiest to wrap your head around. When we are reading direct bitmaps, and I'll pull up the page here so you can see, we just use width times height to scan that number of bytes from csg1.dat at the start address each time. And each of those bytes is going to be an index into the color palette. So let's take a practical example here. I've already found a direct bitmap. I'm in csg1i.dat, which has all the TGraphicRecord records. This one starts at address or offset 6A96. Remember, this is a little endian in csg1.dat. So let's go to offset. I can't remember the keyboard shortcut. It's Control-G. Okay, I should have definitely known that. And I've also already forgotten what offset I said. 6A96. 6A96. So this is where our bitmap data is going to start for this particular bitmap. If we look at what the width and height are, so the width is here, the height is here, that's 16 by 7. Remember, this is in hex, which gives us how many? I should be able to quick math that anyway, but I closed my calculator. That makes me a little sad, so I'm going to go ahead and reopen it. There we go. 16, oops, except I want to be in decimal. It gives us 70 altogether. So we're going to read from this, starting at this address of 6A96, we're going to read 70 bytes, which, or I keep doing that. It's 112 bytes, 70 hex. So I'm going to keep going down until I get 70 hex in length at the bottom middle part there. You'll see on my hex editor here. So right here is our color data for this particular bitmap. And remember, these are indices into the current color palette, which, as we saw, is usually, let me pull it up here, the one we dumped from the main game, which is this guy right here. Windows image makes it blurry, but that's what that looks like. So if we look at this, and here's the image, by the way, and you can see this kind of very clear as day once you have all three of these up. If I could get them up in a logical way here. There we go. Just had to do some Windows maneuvering there. So again, these are indices into this palette right here. That's what these values represent. Each byte is an index. So all these zeros are this first entry in the palette, which is pure black, which is what you see right here. As we get along, we get into hex 72, which is 114. So I'm not going to count all these little pixels, but that's somewhere in a, yellowish region here that it's getting this color. Maybe that guy, I don't know. But you can see that only a few pixels in the top are colored and then followed by several black ones. And in fact, I'm surprised this one isn't a compact bitmap. Maybe there's a reason I'm not fully certain of that it's a direct bitmap. We'll talk about why I think that in a little bit when we talk about compact bitmaps. But anytime you have, very few colored in pixels over a black background, sometimes it's easier to use a compact bitmap format. But regardless, they used a direct bitmap. And so it's really easy to understand this. It's just you read all these index entries and then you pass. I'll go back to the Python code here. We take in, remember this color table data is just the data from csg1.dat. We read that in as a list of bytes. We go to the start address, which is again 6A96, and we read from that address to that address plus the width times the height, which was 112 bytes. And we just take that data, return it back with the width and height, and then the image library we'll use later on. We'll just take that and make sure it renders in the right number of rows and columns of pixels. Right here, you'll see that we do the conversion from, remember that these bytes we're reading from csg1.dat are just the indexes or indices. We take the color palette data right here, and we return a list of what actual color representation is in the palette for that index. So what that looks like, we'll look at in a little bit, but basically that's going to be like an RGB tuple that comes back out of that color palette. That's going to be put into a list, and that's going to be passed to the image library, which is going to write all those RGB color tuples into the image. And then right here, we just make the file name based on, again, the start address, the decimal format, and the hex format. So again, direct bitmap's pretty simple to understand. I'll come back to compact because I want to touch on the second easy one, which is the palettes. And if we go to the site, I've also put this in the comments for the script, but you can see it here. The palette just, we read the width, and that tells us how many 3-byte entries of BGR bytes will be obtained. And you'll see that the starting index for the palette entries is determined by X offset. What exactly does that mean? Well, let's talk about that. All right, so I've restarted RCT. I've gotten back in the debugger and broken at this stretch DI bits call, which, if you'll remember, this is going to be our pointer to the DIB. This is going to be our pointer to the BITMAPINFOHEADER Struct, which has our 40-byte header followed by the color palette or the color table. I'm going to use those two interchangeably, by the way. So if you remember, I briefly talked about comparing that section in RCT to that writing hot games for Windows PDF, where there's an identity palette that's made. And let me see if I can actually find that document again so you can see the code that they include. I had it pulled up here and I closed it once I started making this video. So let me pull that back up. We'll go back to the identity palette section. There's some code, example code here, where you can see the concept behind the identity palette is just to take the number of colors that we're going to use in the color table, which for us is going to be 256. That's how many we use for RCT as well. And you basically just iterate through those colors and make a identity palette of just 000, 111, 222, all the way up to 255, which is from working from black to white, basically. And you can see that reflected down here. I have the color palette pulled up, 000, 111, 222, etc., all the way up to the 10th entry right here, which is something different than just AAA and hex, which would be 10 to 10, 11, 11, 11, 12 to 12. So when we talk about, actually I'll go back to this page. When we talk about the starting index for the palette entries is determined by X offset. The starting index is what index in the current color palette that this kind of inserted palette is going to start at. So for example, the color palette we're looking at in the debugger right now would have an X offset of 10 because we're starting the entries from this palette we're inserting at the 10th element of the identity palette that the game started with, basically. So we're basically inserting another palette within our palette right here. And you can see this inserted palette goes all the way through up to, up to right around here, it looks like, where we go back to the identity palette and we see F6, 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 F7, 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 F8, F8, etc., all the way through to FF, which is 255. So that's what that X offset is. It's telling you where in the identity palette we're going to insert this current palette. So let's go back to the code here, and we see that we have a BGR triad size. So we're going to be reading 3 bytes from the csg1i.dat file. In fact, let's go ahead and find real quick a palette we can use here. There we go. We have a good candidate for palette at address 7682D in csg1.dat. Here in csg1i.dat is that TGraphicRecord row for this entry. You can see it's got a flag of 8 indicating it's a palette. We have the address, and then we have a width of EC. And remember, the width is not bytes like it was, or how many bytes times the height that we're going to read like it was with the direct bitmap. For the palette, the width indicates how many 3-byte entries, blue, green, red, will be obtained from the file. And then the starting index for the palette entries is, like we talked about, determined by X offset. For this one, that starting offset is again number 10 for X offset, so it's going to be inserted into the 10th entry, just like we kind of talked about the one that was in the debugger a moment ago. What else? I think that's it that we need from csg1i.dat. So EC, again, that's the width. That's how many 3-byte entries we're going to load from here. So when we go over to csg1.dat and look at this, we're actually going to be reading EC times 3 bytes. So EC times 3 is going to be 708 bytes of data from CSG1.dat, because again, EC, or what was it, 236, is how many BGR triads there are in here. So this is the, if we're starting at the 10th index in the color palette, the 10th index should be 232317 in BGR, which means in RGB it's going to be 17 hex for red, 23 for green, and 23 for blue. Now we can check that with the output from the script here real quick and just validate that the 10th entry here is going to be 172323 in hex. This, by the way the script generates it is by making an identity palette first and then inserting the palette we're reading from CSG1.dat as the game would. And so we'll start here. Let me just go and blow this up. If we move over to our, I'm going to get the eyedropper tool and move over to the 10th entry. Well, first of all, I guess if you look at the 0th entry and look at the color wheel, it's all zeros because it's zeros. It's the identity palette. The next one should be 111. We see that reflected. So the 10th entry should be the first one of our inserted palette. So this guy right here. And that color is indeed 17 red, 23 green, 23 blue, which is what we would expect based on this first entry. And so our inserted palette is going to go all the way to the, 236 or 235th entry in here, which is going to be all the way down here. And let's see what this last entry here from our inserted palette is before we return to the identity palette, which is, we return there at F6, F6, F6. So the one right before that is 27 red, 3B green, 97 blue. If we go back to CSG1.dat, we can indeed confirm that the last blue, green, red triad we read from here is 973B27. If we flip that, 27, 3B, 97. So that's a cool way, after the script is done, of course, we can run it and validate that we're getting the right data from CSG1.dat. So that's how the palettes work. We're basically just reading the width to see how many three entry triads are here in the order of BGR, and then reading that much data, and that's reflected in the code here. We take, let's go over this from the top. So we know that the triad size is going to be 3. I chose to render the palette images in a 16 by 16 bitmap. I think that looks nice and neat. Since we're using 256 colors, it only made too much sense to make a nice square. We then build an identity palette. So we basically take the palette size here, which is just 16 by 16, multiply it to get 256 numbers. And so from 0 to 255, we're going to make a list of RGB quads, and we're going to convert them to RGB tuples. So again, remember, we're passing in 000, but we're going to reverse that. That's going in as BGR. We're going to reverse it as RGB and turn that into a list of RGB tuples. Let's see. So once we have the identity palette, we then take the CSG1 data. We again go to the start address, and then we read from start address to 3 times the width from TGrecord, which is the TGraphicRecord record. So again, that's the equivalent to saying 3 times this guy, which is EC in this entry, hex. And again, we turn these palette entries into a list of BGR and then convert to RGBQUAD structs and then get them back as tuples. And then what we do is we basically just, this is a little trick, Pythonic trick here, to take the entries from CSG1.dat data, we zip them, and then put that into a list. And what that looks like, let me see if I can get a good example going on down here. There we go, that'll do. So when we read this data from CSG1.dat, we're going to get it back in a byte string, basically. So it looks something like, excuse me, something like this. When we do, let's break this up into pieces, actually. So I'm going to rename it, or I'm going to name it palette entry so that we have it the same as up here. When we do this zip command and we do a iter on palette entries times 3, what that's going to do is, well, let's do it this way. Let's say for a and zip print a, it's going to give us a nice 3-element tuple for every 3 bytes in that long byte string. It's basically breaking that byte string up into 3 elements and then separating them out into a tuple. And then we convert that back to a list because right now it's an iterator. So let's do that last command again, except add list to it. And we get a list of those tuples. And then we use enumerate to get that same list and an index for each of the entries there. So whenever you use enumerate like that, it'll come out looking like, there we go. Sorry, I messed myself up there. So for each index and element, when we call the enumerate function, it's going to break this list out into an index value right here, and then the element itself at that index. And so we use that to basically go through, and in the palette data, in the identity palette, we build it right here. We go to the X offset, which remember is going to be the first entry from the inserted palette that's going to go into the identity palette. For us in this example, that is the 10th entry right up here. And we're going to write the data that we just got from the csg1.dat file that represents the palette. So at that location, or at the X offset plus the index of whatever entry this is in the palette, the inserted palette, we're going to generate an RGBQUAD and again cast it to a RGB tuple and insert that into the identity palette. We'll then take the width and the height and the palette data, just like with all the other bitmaps, and the same file name format, and return that. So hopefully that little example helped paint the picture, no pun intended, of how these palette entries are inserted into the identity palette and how we read those from csg1.dat. All right, good 2 out of 3. The third one is the compact bitmap, which as you can see from the number of comments here, is going to be the most intensive to explain. So let's dive into it. Let me clear my window here so we can start fresh. All right, so the very first TGraphic's record in CSG1i.dat is actually a compacted bitmap. You can see that with the flag of 5 right here, and here is that image right over here. Now, I'll go bring up the page from James's site here where he talks about compacted bitmaps. I'm going to read what he writes first, and I'm going to break this down to you. Compacted bitmap, start address, as usual, which for us is going to be 00000, the very first entry, points to a table of row start offsets that are word wide or 2 bytes. You can jump to start address plus row start offset to start looking at the data. Each row line consists of 1 or more scan elements. Each scan element begins with a 2-byte header. The first byte indicates the number of bytes of data for that element. In addition, the most significant bit of the first byte is a flag. If it is set, this is the last scan element for the row. If it is not set, there will be another scan element following this one. The second byte of the scan element header is an offset value. The scan element begins at that offset from the left edge of the graphic. Pixels which are skipped are to be transparent. To illustrate, and then he talks about the same image that I poorly drew in the first part of the video, which was that vertical 2D ladder. Let me try to break this down using this image with what he's saying here. So again, CSG1i.dat, we start at address 0. We know this is a compacted bitmap. We have a height or a width of 10 hex, which is 16, a height of 7. When James is talking about the row start offsets, what he means is that I prefer to use the term scan line because I think that for some reason in my mind helps me visualize this better. If you think of each row of pixels in this image as a scan line, the height is going to be the number of scan lines for this image. So for us, again, that's 7. And you can see that reflected in paint. We have 0 through 6, which altogether is going to be 7 rows of scan data. So these 2-byte elements we see, to find out how many 2-byte elements we should read from the start of that data, when he talks about these are word wide, when he says word wide, it means they're 2 bytes. These are offsets. So, and again, we're in Little Endian, so we're reading this kind of backwards. So 000E means that the first scan element data starts at E hex or 14 bytes away from the start address, which again is 0 for us. So that's going to be at the element right here. So this is the first scan elements data right here. Now, how many bytes do we actually read from that? Well, we have to read on further to discover how big the scan element actually is. All these bytes tell us, leading up to the scan element data, are where after the start address they appear. So the next scan element is going to be at location 14 from the start, which is going to be right here. So this all the way up to here is going to be our first scan element's data. So again, to run that back one more time, not to over-explain, but to just make sure that's clear. Each of these 2-byte entries is going to be an offset from the start address of the bitmap. Now, note that the number of 2-byte entries is equivalent to the height of the image. So we have 7 scan lines. We multiply that by 2 for 2 bytes each, and we get 14. So we're reading 7 2-byte offsets representing the number of bytes from the start address of the bitmap to the entry for that scan line. Again, we're going to keep going. Hopefully it'll keep making sense. I know it sounds really crazy and convoluted right now. Let's stay with me. Stay with me. All right, so the first one starts at offset E, which is right here. And like I said, we go until the next offset, which is offset 14. So this is the data we're looking at in the first scan element. When I say scan element, what does that mean? That is the data in the image that is not transparent, meaning the colored part of this first scan line right here. So again, back to what James said. Once we get to this data from the offset, each row line consists of 1 or more scan elements. Each scan element begins with a 2-byte header. So this 8406 right here is actually a 2-byte header. And the header, the first byte indicates the number of bytes of data for that element. Let's just stop let's start right after that. In addition, the most significant bit of the first byte is a flag. So what that means is, see right here, bring up a calculator. So 84 hex. That's the first byte we're reading from this scan element data here, 84. You'll see when we look at the binary part of that, the most significant bit, the leftmost bit here, is set, meaning that this is the last scan element in this scan line. So what exactly does that mean? Let me pull up a blank image here to demonstrate this real quick. I'm going to use the ladder example one more time because I think it serves the purpose very well. So let me try to demonstrate this a little better with blocks this time instead of like I tried to freehand it last time. So if there were more than one scan element in a scan line, what that would look like is, let's say we have the ladder example. We have 1 pixel that is colored in right here. That is one single scan element. Later on in the same scan line, let's say we have another scan element, which might be, well, actually, let's go down. Let's draw a little bit of ladder first, because I think this will make more sense. I'm still not doing a great job of making good squares, but you get the idea. Let's say we get down to the part of the ladder that has a little step across it. The first scan line only has 2 elements, which are the 2 sides of the ladder. So this is the first scan element of the first scan line. This is the second scan element of the first scan line. So there's 2 scan elements. Once we get down here, we have multiple pixels colored in for the step across the ladder. Now we may have, I don't know, let's see how many we get across. Again, not a good drawing here, but we have 1, 2, 3, 4, 5, 6, 7, 8-ish pixels in this scan line. That is a single scan element because it's contiguous. There's no transparent pixels between these pixels right here, even though I didn't do a good job. Let's just draw it like this. There we go. Make it look better. Whereas up here, we have 2 scan elements because we have 1 colored in pixel followed by some transparent pixels followed by another transparent pixel. Those transparent pixels break up the scan elements. So we have 2 scan elements. This is one big scan element because there's no transparent pixels in between any of these colored in pixels. And again, the ladder would continue. Now this line's going to have, again, 2 scan elements because there are transparent pixels between them. And then maybe we have another step here, 1 scan element. So with that said, let me pull back up the image we're looking at. don't save, zoom in here. And let's go back to the hex editor and try to trace this through. So again, in our first byte here, we've read 8.4. The most significant bit is set. And remember, James said that most significant bit is a flag. If it's set, this is the last scan element on this row. So that means this row only has one single scan element because it is set as the last scan element. It's made up of how many pixels? Well, if we look back at the page, the first byte is the number of bytes of data for that element. And so if we ignore the most significant bit, which again is just a flag, we are left with 4 in the rest of the data here, which tells us that we have 4 bytes of data for this element. And so there are 4 pixels in this single scan element, and it's the last scan element, meaning there's no other colored in pixels separated by transparent pixels in this row. In fact, you're going to find in this image at least, every scan line is only going to have one scan element because there are no black holes in this image, if that makes sense. So like if one of these was colored black and these pixels were separated somehow, like right here, that was a bad example. Let me try to do it with just a pencil here since I'm working on the pixel level. Let's say these were divided in the second row. These 2 colored in pixels were divided by some transparent pixels. That line would have 2 scan elements, 2 colored in portions that are separated by transparent. But because they're all contiguous, they're all attached to each other, there's only one scan element. Hopefully that makes sense. We'll keep going. And if it doesn't make sense, I think it will once we solidify the rest of the data here. So again, first byte is telling us 2 different things. Number 1, if the most significant bit is set, it's telling us it's the last scan element for this scan line. And the other portion of this outside of the most significant bit is the size of that scan element in pixels or in bytes, whatever way you want to think about it. So again, this has 4 bytes, and those are the 4 bytes you see right here. Remember that this is a 2-byte header. You go back here. Each scan element begins with a 2-byte header. So we read the first byte. That was our flag/size. And then the next byte is an offset value. So this tells us how many transparent pixels precede the colored part, the scan element itself, which is for us 6. So there's 6 pixels here. If we read across, there's the 5th element, but we start at 0, so that's the 6th. And then our scan element starts getting colored in. Remember, our scan element's 4 pixels, so we're 1, 2, 3, 4. And then the rest of that scan line, because this is our last scan element, is completely transparent, or black in this case. And for the pixel data, so now that we've read the 2-byte header, we're now at the actual data of the scan element. This is, again, just indices into the color palette. So at hex 49, which is the 73rd entry in the color palette, I don't know if we can validate that with one of the other. I don't have it pulled up, so I'm not going to do that. But these are just the regular indices into the color palette that we've seen used in the other bitmap formats here. So one more time to recap. Sorry if I'm being a dead horse, but I know this was really difficult. My brain basically made the do-do-do-do sound as soon as I read this the first time. I had to read it multiple times over. To recap what we did here, we went to the address specified in CSG1.dat for this compact bitmap. We read the height times 2 bytes worth of offset data. So 7 times 2, 14 2-byte values, which tell us the offsets from this start address to each scan element. We saw the first one was at offset E. That was right here. We read this first byte and saw that there were 4 bytes of color data, color indices. The most significant bit of this was set. And so we knew that this was only the last scan element, and so only one scan element in this scan line. The second byte told us how many bytes of data, or I'm sorry, no. Second element told us how many transparent pixels preceded this colored part. So 6 pixels from the left is where our colored part began. Here, these 4 bytes are pixel data or color data, the color indices. And now, right here, we start our next scan element, which again is at offset 1.4. It tells us right there. This one has a size of 8 bytes. So we remember we need a 2-byte header plus 8. 1, 2, 3, 4, 5, 6, 7, 8. Again, the most significant bit is set. So this is our last element in this line. And there are 4. Is that right? 4? Yeah, sorry, I'm reading up here. 4 transparent pixels that precede it. So from the left, we count 1, 2, 3, 4 transparent pixels, and then we start drawing our colored section, and then whatever remaining data is in that scan line is going to be transparent. If you grasp that, then the good news is you basically mastered the hardest part of this video. The hardest explanation is that compacted bitmap. So let's go over to the code, and let's see exactly how this is implemented in the mod code. So going to the generate compact function here, again, we take in the TGraphicRecord, the palette data, and the color table data from CSG1.dat. First, we read the header containing the offsets to each scan line row. So that is, we are reading this part right here. And remember what I said, 2 bytes per scan line. So we just take the height of the bitmap, which we got from the TGraphicRecord, multiply it by 2, and in CSG1.dat, we read from the start address, which in this case is just the very first one, 0, 0. And from the start address to the start address plus 2 times the height, which is going to be this data right here. We then use the iter_unpack function from the struct package here. And if you haven't used that before, I messed up the formatting here. Ignore my bad error right there. How that works is, so like this example right here, we pass in a format string and then a string of bytes. In the Python documentation, you can see that the format string basically indicates 2 different pieces of information, actually. The first character you saw, which is that left-facing caret there, means that we want to read this in little endian format. So again, remember, all this data is in little endian, which means we want the Python script to read this as if it's 000E, not 0E00, if that makes sense. And so that caret to the left means that we're going to read this in little endian format. The second character tells us how many bytes to read. And here's the different characters and their formats. We're reading 2 bytes, so I used a capital H for an unsigned short. In this case, well, yes, actually it could impact us if we use a signed short because we don't want to interpret these as any negative numbers. So I stuck with an unsigned short. Yeah. So with that in mind, what this iter_unpack does, so let me back up. Unpack by itself just reads a single value. So I'm telling it, read a little endian 2-byte value from this hex string here. So again, that's 0E followed by 00. And then Python has used little endian, so it's flipped that to just be 0E, which is 14 decimal, and it's returned that as a tuple. So I really just need the first element of that tuple to get the value I want. I'll talk about that in a second. First, I want to talk about iter_unpack. Iter_unpack works exactly the same as unpack, but if you pass it a string of multiple values, so in this case I just made up 6 bytes here, 0E00, 0F00, 0A00, so 14, 15, and 10 in hexadecimal. And I say, hey, read 2-byte little endian values from this string until you can't read anymore. And so it did that. It turned it in, or I converted it to a list. And so we read in little endian format 14, and then 15, and then 10. So that's what iter_unpack does. Now, I took the extra step up here, and I'll demonstrate that down here. What you actually want to do, since this is returning a tuple from iter_unpack, you actually want to make a list and go for, or we'll say element 0 for element in that iter_unpack result, because we don't really care about interpreting it as a tuple. We just want that value that it returns. And so doing it this way, where we just take the first element of those tuples, means we just get a list of values back. So that's what we're doing right here, is we're just reading in the offsets. And it looks something like this for 14, which would be this guy right here. But I made up the rest of the data for this example. I just wanted to show you what that looks like for unpack and iter_unpack. Excuse me, I need a drink real quick. All right, so once we get the offsets, we're getting ready to read the actual color data. So we set up a list to hold that data. We make a flag right here called last element to flag whether or not this is going to be the last scan element in that line. And then we make a list here, which we're basically just using this as a placeholder for each scan line, which we'll insert the colored data into. So let's see how that works right here. For each scan line in the offsets, if we've reached the last element, we'll go ahead and write the scan line, the full scan line that we've already, inserted all the colors into to the data list here. And then we'll make a new scan line that is just made up of transparent elements times the width. So what does that mean? So again, a transparent element is just black 0, 0, 0 times the width. So basically we take a whole row of black pixels, however long the image is. In this case, it's what did I say? It was 16? Yeah, 16 pixels long. And we take a whole, row of 16 black pixels. If this is the last element, so let's say we've already gotten through one loop of this and we've written this color data here and the flag is set that this is the last element, we go ahead and add the scan line to our complete data set as the first scan line. Then we start a new scan line that is just made up of transparent elements times whatever the width is. So we start with a black line basically. We get the start of the element by adding the offset to the start address. So we're taking, in keeping with our same example, we take the offset, we add it to 0, 0, 0, 0, we go to E, and then we start reading our data there. So we take the first byte from that location, we check the most significant bit right here. I'm calling that first byte, by the way, the meta byte because it's giving us some metadata about the scan element. We take that first byte, we AND it with 7F. So let's take 7F, and you can see that's all ones except for the most significant bit. We AND, let's take 8,4 with that, and we get 4. So if that most significant bit was not set, so let's say we just have 4, and we AND it with 7F, we're just going to get the 4 back. So regardless of if the most significant bit is set or not set, this part right here is just getting us the lowest 4 values of that byte so that we know how big the element is. And then we take the start of the element plus 2 to account for the header plus element size data. So what that looks like is, again, we're calculating the end of the element. And so we start at the offset, we add 2 because we want to skip over the header. And then we read 4 bytes here, which we just calculated right there. And so that gives us the end of the element, beginning of the next element right here, or the next scan element right here. So the byte after the metabyte is an offset from the left edge of the bitmap. So we calculate the offset from the left by, again, if our cursor, so to speak, is right here, we just add 1 to the element start. We get this byte, and from there we read that as the offset from the left. And we read the element data as element start plus 2. So skipping past this little header right here, we start reading here from element start plus 2 to element end, which we calculated right there, which was around 4 bytes of data right there. For each byte value we have in this data right here, we take the scan line, we take the offset from the left that we start at plus the index of the element. So for example, let's say, what is our first element here? 49. So we take the value 49, which again is a color index into the color palette. We take that color in the scan line, which is full of black pixels right now. We say, okay, my offset from the left for this line is 6. So at scan line element 6 plus 0 in this case, we're going to set this to the first value from the palette, which is some green color right there. Hopefully you're following along here with this logic I'm using here. I know we talked about the enumerate function already, so if you don't fully understand that, what that is doing is just giving us the index as well as the value in this element data list so that we can calculate offset from left plus that index. So again, for the first pixel of the scan element. Let's go back here. Offset from left is 6. Element index is 0. So at element 6, which you can see in the bottom left corner here, is going to be green. When we get to the next color index, so in our hex value, this guy, 49, again, right here, we are now at still the same offset, 6 plus element index 1. So now we're at the 7th pixel of the scan line. And so you see we're basically overriding pixels of that black scan line as we go. And the last thing we do is we come back to that metabyte and we AND it with 80 in hex, which will just give us the most significant bit. If that is not set, so let's say if our first value here was just 4 without the 8, that means that, excuse me, this is not the last element in the scan line, and so we should keep reading scan elements. But since it's 8-4 in this case, that means the most significant bit is set. When we AND that with 7 or with 80, we will see that it's greater than, what did I say the first time? If you AND it with 80 and it's not set, it's going to be 0. If you AND it with 84, it's going to give you some value that's not 0, basically. Excuse me. And so when we go back to the top of the loop here, since last element is basically equivalent to if this is anything other than 0, go ahead and write that scan line to our complete data set here, move on to the next scan line right there. So hopefully you followed along with the logic here. What I recommend if you're still not getting it is take the script from the GitHub repo and start making some logging statements here. So if you want to, for example, you could start by doing a logging.info and just write the scan line to the screen. Log each value as we go down here. And of course, you'll have to import the logging library here in the script here if you're doing this. But if you do that and you want to take a deeper dive and see all the different values as they are iterated over, you can do that using the logging library or just using print statements as well. You could do that as long as you take them out again once you're done. Again, compact bitmap, a little difficult, especially compared to the other two types of bitmaps we have to wrap your head around. But once you understand what the different values we're reading are, it's really not that difficult once you fully get, I just said it's very difficult, but it's not that difficult. Sorry. What I mean is once you've done it a few times, you've iterated through and you see the pattern here, then you realize, once again, we're just reading color palette data indexes from the data. The compact bitmap just does it in a way that it saves space so that it doesn't have to keep reading a bunch of black entries followed by some very few colored entries in the image here. All right. Again, if you made it through this far, congratulations, you've gotten through the hardest part of understanding in the video. The rest of the code is going to be fairly straightforward. Also, I guess I didn't wrap up. The bitmap for compact bitmap, the return for this is very simple. It's just the width, the height, the full scanline data, which is just the pixel data that we read, and the same file name we've used for every other color. And that takes care of the bitmap class we've got here. So now that was our last struct that we walked through. Or I'm sorry, we have one more. We have the Windows process struct, which is just a helper file, which uses the PE file library, which you will have to download. It doesn't come with Python by default. What this does is, oh, I'm in the wrong file. What am I looking at here? I was like, that doesn't sound right. Why is PE file being used in the Windows process? No, psutil is the one I'm thinking of. psutil does not come by default, but it is in the requirements file for this repo. And so you can do a Python tech-m pip install tech-r requirements, and it will install all these libraries if they're not installed already. Obviously mine should be installed, and so it's going to say, hey, this is already satisfied. But yeah, psutil does not come by default. Neither does PE file, but we'll get to that one later. And we're using one function from the psutil library, and we'll get to that in a second. We're also importing C types, which does come with Python by default. And we're using that because we're going to basically use this file to read from a Windows process in memory. Specifically, obviously, we're going to read the RollerCoaster Tycoon process. The reason we're doing this is so that when we do the dump or show command where we're reading the DIB and the palette information directly from RCT, we're going to open the process that's running, and let's just run down it right here. This is just a constant to keep track of the permissions we need for, basically the permissions we need to open the process. We only want to read it in a read state. We don't want to write anything to the process. We're just reading from it. And so in the constructor here, we just take a process name. We find the process ID or PID of that process by iterating using this process iteration function from the psutil library. We iterate through all the running processes. We find the one that matches our process name, which in this case is going to be rct.exe. And we grab that process ID and store it in this object as well as the process name. If we can't find it, we raise an exception. And then the only other function in here is the read memory function, which takes an address and a number of bytes to read. And it uses the Python ctypes library to basically read and open and read, I should say, a Windows process like this, again, using read-only permissions. We use the PID to get that process handle. If we don't get a handle, we obviously raise an exception. Otherwise, we make a buffer, a string buffer of the number of bytes we want to read. Actually, let me bring up the read process memory documentation here so you can follow along with this. This is from the kernel32.dll. So we have the process handle, the base address, the buffer we're going to output bytes that we read to, the number of bytes to be read from the process, and then this last one is a pointer to a variable that receives the number of bytes transferred into the specified buffer. So after we read the number of bytes, we're going to return the number of bytes we actually read. So we're requesting a certain number of bytes to read. Maybe we don't actually get that number of bytes back, so this pointer is basically telling us how many bytes we actually read back. So in our Python script over here, we're recreating that process call. We get the process handle, the address we want to read from, the buffer we want to write to, the number of bytes we want to read, and then this pointer. And then we close our process handle and we return a Python list of how many bytes we read. So from the raw buffer, we read up to the number of bytes read and no further, because if our buffer, let's say, is 10 bytes and we only read 2 bytes, we obviously don't want a bunch of null bytes at the end there. All right, and then we raise an exception if we fail to read for any reason. So again, we'll see this in action once we get to the DIB palette dump script right here. But for now, just know that this is a struct that basically encapsulates a Windows process, and we just use it to read memory from an active Windows process. All right, moving right along to bitmap extract. Now we have moved out of the structs folder, subfolder here, and now we're into the utility scripts under utils here, starting with bitmap extract. So this is the utility script that actually extracts the bitmaps from csg1.dat using csg1i.dat and a color palette, as well as obviously the output directory that we pass in. Couple of things to touch on with this one. So I did make this multi-threaded, and I'll talk about that in a second. Other thing is PIL or Pillow is another requirement that you'll probably have to download if you haven't installed it already. That's the image library we're going to use to actually write the images to disk using our little utility script here. Yeah, on the topic of multi-threading, some may agree with the approach, some may not. But since we have a scenario where we're reading the raw CSG1 data into memory all together as one block of memory, as well as the palette data, and each bitmap record, the TGraphicRecord, can kind of stand on its own. And because there were so many bitmaps, remember nearly 70,000, and because we are working with data that can operate atomically, we're not making any changes that are going to conflict with each other, I thought this was a good use case to do multi-threading to speed up this process of parsing images out a little bit more quickly, at least. It's still resource intensive because of all the images, but when I did my checks in both time and resources used, multi-threaded came out on top every single time. And so I'm using the Python built-in concurrent futures module to run the multi-threading portion. The reason I mentioned that now is because from top to bottom, the first function we're going to see in this file is the thread-safe function that's going to work with an individual bitmap record. And what it's going to do is it's going to take that BMP record, which is that TGraphic's record. We're going to take the palette data and the CSG1 data, and we're going to pass that through to bitmap, which remember is going to take that and then decide based on the flags in that TGraphic's record, what kind of bitmap to generate. After that, so that's going to return us that full scanline data. If it's compact bitmap or whatever, it's going to return us the bitmap data. I shouldn't say scanline data. It's just the bitmap, data, whatever format it might be in. We're going to use the Peele library to then create a new image in RGB format with the width and height, that we specified. We're going to put that data that we got back from here into that file and then save it to our output directory with the file name that we generated in the bitmap class. If we're successful, we return true from this. If not, we return false, and we'll use that flag or that return value later to determine if we had any issues when we're extracting all the bitmaps. The next function is actually the driver that makes the threads and does all the heavy lifting here. So if our output directory does not exist, we go ahead and make it for the user. We parse the palette from the passed-in palette file by just using the Peele library to open it and convert it to an RGB dataset. And, that doesn't convert it to, that converts it to like image data, and then we use the get data function on that image. We convert that to a list, and that basically gets us it gives us a list of RGB tuples from that data file, basically. Let's see. So then we parse the TGraphic's record from CSG1I. We open that file as a read binary, and then we iterate through each row. Let's see. So this is I'll spend a little bit of time talking about this. Back in the TGraphic record and some of the other struct files, you saw that many structs had this format string as a constant in them. That is the format string we're going to use with either the unpack or iter unpack function from the struct module we talked about before. So in this case, we are reading, let me pull up that page again so we can follow along in the documentation. Little endian, little endian, capital L is an unsigned long, so 4 bytes. And then 6 of H, which are 6 2-byte values. So the reason we did it that way is, if you remember, the TGraphic's record has a start address that's 4 bytes. That's the first 4 bytes, the L we read, followed by 6 2-byte values, all in little endian. So that's what that's saying, is unpack those values iteratively and then generate a TGraphic record from that data. Now remember when I talked about this asterisk operator earlier, this basically takes, if you look at how this is working, so from this iter unpack, we're going to get back a list of tuples, basically an iterator of tuples that are going to be, the start address, offsets, etc., all the data that's in this TGraphic's record. We take that list of tuples and we basically unpack it right here, and it basically assigns all of those to the appropriate parameters automatically, which is the magic of using the data class here with that star operator. So we create an instance of the class using the record data, unpacking it into all the right members there. So for each record in the file, we generate a new TGraphic record object using that record data. All right, so then we start extracting, and how we do that is we open CSG1.dat, we read that raw CSG1.dat data, we start a success count of how many bitmaps we were able to successfully extract, and we measure that based on the results of each of these threads we're going to create here. So what's going on here is we're creating a thread pool executor. So this is a pool of threads we're going to use, and it's a little bit of shorthand, so I'm going to try to walk you through it. So we're going to use the map function of that pool and the partial function here to call the bitmap dump thread safe function with the palette path output CSG1.data. This all stays the same for each record. All 3 of these stay the same. What this partial call does is it applies those 3 arguments into this function, and then we add bitmap records with the map function here. So basically what this is saying is, it's, to put it plainly, we take each record in bitmap records, and then we pass in that record to bitmap dump thread safe, followed by all these other elements that stay constant from the bitmap record, if that makes sense. And so we count, or we amalgamate all the results that are successful. So if result, basically if true, if this returns true, we add that as a success, and then we count how many successful ones we have, and ultimately output that. So let's go ahead and run this. I think I did a test run here earlier. So I'm passing in my palette, my csg1.dat file, my csg1i.dat file, which again, this comes from program files on Windows from when the game's installed. This is actually stored on disk, but I copied it over. And then this is my output directory. So let's go ahead and run this. And it's going to take, even with this somewhat powerful laptop I have, it's going to take a good minute or two. Oh, not a minute, maybe just about a minute to parse all 70,000 of these. And again, they're running all in their own thread. Each bitmap has its own thread. There we go, 69,917. If you want to check to see how many we should have extracted, you can always look at csg1i.dat and look at how many rows are in here. And so if we look at, what is that, 1111 C0, that should be, what is that? Oh, sorry, divided by 16 because each one's 16 bytes. Sorry, there we go. 16 decimal 10 hex. Yep, 69,917 because again, we need to count the 0th element here. So yes, that's exactly how many bitmaps we should have. And again, I just overwrote the ones I already made. If you look in the folder, there they all are in all their glory. And it's truly fun to watch through some of these and look at all the different angles and animations that they have in here, and all the different assets. There's so many assets that I never came across while playing the game that I discovered that were in here that I still have no idea how you get them. I'm sure I just need to play more instead of, I think I was reversing it. Anyway, that's it for bitmap extract actually. So pretty straightforward. We'll go ahead and close that out. Next is DIB palette dump. So this is used for both the show and dump command. So remember, oops, not this one, but this one is one I don't show. Show and dump both call the same functions. The only difference is that dump writes the two files, the palette and the DIB, to disk, while show just displays them for the user. So let's walk through that. We're going to use the process dumper script here as well, which we'll get to that in just a second. But let's take a look at what we have in this DIB palette dump file first. So this offset constant here is hex 88. And if you're wondering where that comes from, that's the offset to the bitmap info struct pointer after the DIB. If you remember from the part 1, there we go. I'll pull up the debugger again so we can see this in action. So if you remember, this param1 is a pointer to our DIB. And when we add 88 hex to that, that's going to give us our address to the bitmap info struct there. So EAX currently is 2DE0A90. If we add 88 to that, we get 2DE0B18, which is right here, which is going to be 2DD2348, which if we go to that in the dump, that is the start of our bitmap info header struct followed by the color table right there. So in our code here, that offset is just the 88 that we're going to use to add to wherever our pointer to the DIB is there. And speaking of, here is, if you remember, the address we discovered was the holder for the pointer to the DIB. And if we look in our debugger here, let me go back here, copy that, go here, we'll go to a different dump view here and go there. So that address has a pointer that takes us to, you guessed it, the one we just looked at, which we then added 88 to right there. So the next two values we talk about are the resolution of the window, which we didn't talk about in part 1 too much. But if you remember, if you pull up stretch DI bits here, we pass in the source width and source height and desk width and desk height, which for our purposes are basically going to be the same to stretch DI bits, and you can see them in the window here, right above where our pointers to the DIB and the bitmap info struct are the hex values of the resolution of the window. So we have 280, which is 640, and then 1E0, which should be 480. So where did those values actually come from? Well, if we look at how or where they're pushed onto the stack in the function that calls, this draw to canvas function as we called it, let's see where those come from. So if we return from this, here's where they were pushed on the stack right up here. And this is where those two values come from. There we go. Let's set a breakpoint right here actually so we can watch this in real time. So right here, we move C3, E2, E4 into EAX and then push it onto the stack. That's our width, 280 hex or 640 in decimal. And then we move C3, E854, which is 1E0 hex or 480 decimal. And again, move that onto the stack. And then eventually we will call the function, I think it's this one down here actually, that in turn will call stretch DI bits, yep, down here. So again, that's where those two values came from, and that's how they're pushed onto the stack right before we get to stretch DI bits, which is all the way right there. There they are on the stack right there. So those two addresses have our window resolution, and we'll use those to get the current DIB and write it to an image file. All right, and then of course our target process name is always going to be rct.exe. So this is all just one function in this script. This sets the show command. So if the user passes in the args.command as true, sorry, let me rephrase that. If args.command is equivalent to the string show, then we set this equal to true. If the palette and DIB paths are specified, then we will we'll make sure they're captured here. Otherwise, we'll write them as none. We then use a process dumper object to, and we'll get to that in the next file here. We use that to basically calculate all of our dynamic addresses for us. So it locates the DIB using that process dumper. It locates the bitmap info struct, bitmap info header. It shows us the values of the bitmap info header. It shows us where the color table is, the resolution, and finally it generates those two files if the user requests it. So if this is set to show only, it will not save any file. If it's set to not show only, then it will save it to whatever path is passed in here. Same goes for the DIB. So the show command looks something like this. And I think I still have RCT running, so this should hopefully work. It's not going to write anything to disk, except for a temporary file, of course. This is blurry because of Windows, but if you go into the edit view, it becomes a little bit more clear. That's a palette image. And there's the current DIB that's on the screen right now because I just have it idling on the menu screen there. And you can see all that metadata we dumped out from the process dumper right there. So this just does the actual, this is basically a runner for the process dumper and does a lot of the high level logic for that file. So let's move to that file next. This one was pretty straightforward, I think. All right, now we're in process dumper. Again, we specify a constant palette size because this is also going to generate a color palette, and we're going to write it to a nice 16 by 16 square. So we take in the process name. We're going to use that Windows process struct we looked at earlier to get that PID and read memory from that process. And then we have, before I get further, let me go down and show you this function unpack from process memory. What that does, it's all the way down here, is it takes in an address to read from, the number of bytes to read, the format to read from, which is by default little endian and L, which if you'll remember is that, excuse me, unsigned long with 4 bytes. As iter is just a flag that says if we want this to use the iter unpack method, e.g. we want to continuously unpack methods or values until we cannot anymore, we'll set that to true. Otherwise, we'll just use the regular unpack to unpack a single value. And then we'll use whatever function we selected to, and the format string we selected to read from that target process at that memory using the read memory function we went over earlier in the Windows process struct. And remember, this is going to fail if we're running in full screen mode because the method that we use to read the DIB and the bitmap info header are not going to be the same if we're in full screen mode, which is why you have to run RCT in windowed mode for this to all kind of work. But the script will tell you if you're not and warn you that this is not going to work. If we are only reading a single byte, we don't want to return a list with just a single element. So this is just a little check to make sure that we don't return a list if we're just reading a single element from memory. All right, I just wanted to explain that before we get any further so that we can see when we get up here and we're reading pointers from memory, we first take the pointer to the pointer to DIB that is passed in, which if you'll remember from back here, that is this guy right here. So we read that, we read the data from that address, which again, by default, we only read 4 bytes in little endian by default. And that's going to give us the address for that pointer to the DIB. Next, we get the actual pointer to DIB by unpacking that same address, and then we get the bitmap info by unpacking that and then adding that offset to the bitmap info struct, which is this guy right here. Then we use that bitmap info header struct we looked at earlier, and we take the binary data from this pointer in memory. The size of the bitmap, let me go ahead and open that struct up so we can follow along here. The size is 40, remember, that's the size of the header itself. We use the format string from the class, which is this guy right here. Again, we have 3, let's break this out really quick. We have 3 bytes of signed longs. We have 2 bytes of signed shorts, and we have 6 bytes of, oops, don't do that, of, again, signed longs. That's the format of the bitmap header struct, and I don't know, do I still have that up? Yeah. That's basically copying all the values that are right here. We have 3 longs, 2 words, followed by 6, essentially, longs, again, 4 bytes, 4 signed bytes, I should say. So that's what we're reading from memory, from the process in memory here. We're going to that bitmap info pointer that we just dynamically calculate, and we're reading the data from there. And that's going to give us our bitmap info header. We cast that into our custom Python struct, and that way we can easily read all the values from that header, such as the height, the weight, or the weight, the width, the height, the planes, etc., etc. All right, then we get the color table, and remember that is the start of the bitmap info struct plus the size of the bitmap info header, which is 40 bytes. ChatGPT said it was 42. It is not. It is 40 bytes. Then we use another function to build the color palette. So let's take a detour and quickly look at that. So remember, we are just sending in the, let's see. Yeah, we take the bitmap info header. We take the BICLR used member of that. If you remember that member, it is indicated in here that, let me see the documentation. Here we go. The size of the array of RGB quads is given by BICLR used. If BICLR used is 0, then, so that's this case, it'll be equivalent to BI bit count squared, basically. So that's what this block is doing right here. That's giving us the whole color table size. Again, for us, it's always going to be this value, which is 256. And so what we do is we read all the bytes from that region. We generate RGB quads from that region, and then we convert those to tuples, the RGB tuples. For each tuple in that, in the process memory that we're reading from. So we take the process memory, we get the pointer to the color table. Again, that is, we'll go there in the debugger here so we can follow along. Starting from this guy here and going for 256 values there. Remember, these are in BGR order, right? No, maybe I got that backwards. They might be in RGB order in here, actually. Now I got to find out. Hold on. I'll double check that real quick using our palette that we dumped here a second ago. That's the benefit of having the script able to dump the palette, is I can just open that in, where's my paint window? Oh, that is my paint window. There we go. Open that in there. And let's just check to validate my logic here. So the 10th element is, let's do the eyedropper actually, which is under here. Go to the 10th element. Maybe I need to blow this up to make this easier. There we go. That's going to be this guy right here. That's set to, oh, nope. Did I get the wrong one? 10th element, right? Ugh, I'm such a dummy. I had the wrong color selected up here. So it's just giving you white every single time. I was so confused. Okay, so 10th element right here is, oh, no, that's 999. Let's try one more. Am I just off by one here? Am I taking crazy pills? What is going on? What is my color marker or my dropper not working? Oh my God, I'm using a pencil. Jesus Christ, Jeff. All right, for the win this time, 10th element is, there we go, 23, 35, 35. That's in decimal, or in, yeah, decimal. So 17, 23, 23. Ugh, going back here. Should be in, yeah, it is in BGR order. Okay, I feel better about myself. So 17, or 23, 23, 17, meaning this is BGR. Jeez, sorry about that. I am tired and I don't want to give you guys the wrong information just because of that. So again, we're reading that in BGR order, but then we convert it from RGBQuad to, or I should say we convert it from BGR to RGBQuad right here as a tuple. And that's how we build our color palette. And again, we use the format string from that struct, which is just 4 bytes, because remember we have that reserved byte at the end. And this is saying true, which means if you remember that we are setting as iter as true, which means we're going to use iter unpack to unpack that, because we're reading up 256 and we basically want to read through that 256 byte block 4 bytes at a time. All right, that was a long explanation for something fairly simple. Apologies for that, but hopefully, you know, I always say I want to be more in depth than not. So we build our color palette that way, and again, that's going to be a list of tuples, RGB tuples, because we're using that RGBQuad class there. Then we read in the resolution from memory again, and then we build the DIB using this guy right here. So we read at the pointer of the DIB, the width times the height taken from the bitmap info header times -1. Remember, the height is going to be negative in this case because we have a top-down DIB. And if you remember, if I still have it up, the device independent bitmap page, or maybe it's in the bitmap info page, bitmap info header page. Yep, if BI height is negative, the bitmap is a top-down DIB, which is going to be for us. So we multiply by -1 to make sure that we get a positive number here. And then we take the color palette we just built, and we take the indices we just read from the DIB, and we index into the color palette and return that RGB tuple for each color in the palette. And for this, let's see. All right, so when we're generating the color palette, which comes into play, oh, where is it? Oh, it's actually in it's actually in the DIB palette dump. That's where it is. I'm not seeing it here because it's not in here. So when we generate the color palette, we simply run the generate image function for both of these, actually, the DIB and the color palette. We pass in the size, color palette data, the save path, and if it's show only, we only show it. We don't save it to disk. Same thing here. Now you will notice there's one difference with the DIB, and that's that we crop it, because if we don't do that, it'll actually write out all of the black portions of the DIB as well that aren't actually filled with color data. So we crop it to just the resolution of the window we're looking at right now. And then the generate image is pretty straightforward. We use the image library, the Peele library again, to write a RGB image of our specified size, put the data in there. If the crop is specified, we crop it. If it's only show, we run the show command. We show the temporary file, and then we don't save it to disk. Otherwise, we'll save it to the save path. Still with me? That one was pretty straightforward too, I think, aside from me going on the tangent about the color palette and everything to make sure you understood. All right, that leaves just one, and it is not hard to understand if you watch part 1, but it's probably the longest file we have here. This is the script that actually does the patching of the file, and I guess I should quickly run a demo of before we get into this, the dump command. Pretty straightforward. So if I wanted to dump the current palette, dump it in my project folder here. We give it the palette write path and the DIB write path. And we can open those from, I have it open on my other monitor, but we can open those right from the directory, and there they are. All right, now the patch one. Let's go ahead and run that first and then go through the code, because I'll use the output to kind of walk through everything. So as far as arguments, in fact, I might still have this in my history. Yeah, I do. As far as the arguments, we pass in the input file, the output file. We can do a different bitmap, which we'll do in a second. We'll leave the defaults for now, but we'll do a different bitmap and maybe a different track in a second. But yeah, by default, it'll replace the explosion animation with the skull. And by default, it'll play the CSS25.dat, which is a spooky horror thing. And so I just want to specify for now these two, the input and the output files. So let's run that. Tells me it is attempting a patch. It successfully replaced the bitmap, set the audio track. It found a suitable place to put the shellcode. It wrote the shellcode, patched the call instruction for the shellcode and output file. So let's walk through each of those steps here. Again, I mentioned this earlier briefly, accidentally, that we're going to be using the external library PE file, which we're going to use just to calculate a few addresses here, or offsets. Up here, I have used a somewhat strange, some would call it strange, system of writing out these hex strings. I come from the world of writing detection signatures like in Yara format and other, byte formats like this, and I find this a little easier to read and write than writing like Python byte strings like this and this. And so I did a little bit of extra work to just use this custom format where I can just write bytes in separated by spaces and everything just works. So what you're going to see here are a couple of tuples, or a handful of tuples, that will have a value that we're going to replace and the value that we'll replace that value with. Now, you'll notice some of these have placeholders because we will be dynamically calculating the addresses to put here. So this one, for example, or the values, I should say, not just addresses, but values. This is the location. These bytes represent the opcodes for the instructions that load the explosion bitmap. If you do a search in Ghidra for, let's see, memory for this, it'll take you to this line, which you'll remember is where the explosion offset, the explosion bitmap offset is loaded in, and then the explosion is triggered. So we're going to overwrite this opcode right here, which is what is represented in this this hex string right here. And again, the first two opcodes stay the same. That's the actual instruction for the move into add into EBX. The only thing that changes are the offset, the 4 offset bytes right here, and we have a placeholder for that because depending on what the user puts in, we may have a different offset. By default, it's going to be B94A0. The next piece is the patching of this instruction right here. If you remember, right here. This is the one we replace with our move the shellcode offset into EAX and then call EAX. So that's the opcode we see right here. We're going to replace it with this opcode with this little placeholder here being our offset to the shellcode. And this next part is going to find the region in memory to write the shellcode. Also, I think I misspoke in the first part. I think I said this was in the resource section. It's in the data segment, or the section of the PE. So if you look in Ghidra, for example, you see this data segment here, section here, Jesus. And in this section, as I showed you in part 1, let's search for the bytes here. There's a portion of the memory that has a kind of countdown of 3, 2, 1, 0. And actually, it's not this one, but the next one I just closed there, the second entry here at C412C2, where we have this nice section of null bytes, negative space right here, which is where we decided to write our shellcode, right below here, right? I think it was right around here. Where does the program say it wrote? C412C2, right here is where it begins. Is that right? Ha, that is certainly not right. I actually just caught that bug. I'm glad we're doing this, guys. So in case you're curious what I did wrong, and I'll fix this right after I record this video, and I'll update the repo with all the little bugs I found and little things I cleaned up. But when I go to look for a suitable place to put the shellcode, I just look for this region to make this kind of address agnostic. I just look for that pattern of 3, 2, 1, 0, followed by at least 80 0 bytes there, null bytes there, which is this region right here in the data segment for me. However, I forgot when I'm actually writing the shellcode to add, since I'm looking for the start markers right here for that 3, 2, 1, I forgot to actually add 8 to get past these bytes and start writing at what should be C41 to CA. So I'll show you, it's down here, but I'll show you when we get there that I just needed to add, see I came in right here, needed to add those 8 bytes back so I didn't overwrite whatever that 3210 sequence is, just to make sure we don't mess with anything that we shouldn't be in that data segment that's already got data written to it. Anyway, I'll fix that. But this replacement string is just looking for that suitable region of null bytes to write our shellcode. So like for this shellcode, if you were curious how we get this this hex data, you can use that same site we were looking at in part 1, this assembler disassembler. I'll work backwards, but you can do the same thing working the other way. Just you have to make sure you replace these placeholders with something like DD. We'll just put a placeholder value like ABCD here. That's going to be addresses to our offsets. If we disassemble that hex, it gives us the exact shellcode that we want. But you can also take these instructions and remove, all this other stuff at the front. That's how I initially got the hex code, is just by putting these into here. Obviously remove this stuff, and then just, I won't do the whole thing just because I don't feel like doing this for every single line, but let's just take these few. I worked from the instructions that I wanted backwards, assembled it, and then took the opcodes and put it into hex format. So that's where we'll put in our shellcode. And then again, the placeholders you see here, there's 2 altogether. Those are the addresses to our audio track that we're going to use with MCI sendString, which is going to be that audio library that plays the track or opens it and then plays it. Speaking of, the next 2 constants are the commands or the strings that are just to open our track and play the track. All right, so again, we're using the data seg section to place our shellcode into. So this RCT horror patcher, it was easier to put this all into its own class because there's a lot of data that gets reused and tracked throughout this whole process. So we're tracking the address of our shellcode, the data we are going to write, the in file, which is rct.exe. The data we're going to write, by the way, is the contents of the RCT executable, and then we're going to keep updating this member with our shellcode and our other edits and replacements. And then at the end, we'll take that data and we'll write it to disk. So we read in all that metadata that we talked about. Let's scroll down here. Because I am using this weird format of spaced out hex strings, I have some helper functions here. One of them is byte to hex string, which means if I get a byte string like this, I convert it to a string like this to make it work with the string format I have up here. That's all that is. It's just simple string operation to convert a hex string like this to a hex string like this. Yeah, and you can also use it with the pack method here, which is also part of the struct module. If you remember, we unpacked using the same format. Now we're packing it back. So something like this, if we're reading it from little endian, becomes this. So you see the values are flipped like that. This function is used to calculate the address at which we should write our shellcode. So this gets a little tricky because when we read the data, the binary data into Python, we're going to be working with file offsets, right? So we use the PE file library to do some address calculations here. So for example, we look through, first we read the exe into the PE library as a portable executable. We find the image base, and then we iterate through all the sections of the PE and we look for the data seg section. We take the virtual address, or how do I want to say this, to calculate the virtual address of the shellcode, which will have the offset to the shellcode in the file data itself. But what we want to do to convert that to a virtual address is subtract the file offset of the beginning of this section. So that's pointer to raw data right here. This is the address. In fact, let's do this actually. This is going to be easier to do than explain. Let's just log this real quick. All these values, oops, self.offset shellcode, this guy, and this guy, and I should probably actually be doing the hex version of these. 1 second. All right, let's run that. Okay, we get a little bit of an error because I guess one of those values was not converted. Well, that's fine. It for our purposes, it doesn't matter because this is temporary. But this, we know in the file where the offset to the shellcode is because we'll calculate it. I'll show you where we calculate it in a second. So this is a file offset. This is from the start of the file. How many bytes is it to where we want to write our shellcode? To convert that to the virtual address, such as, what was it, C4, not that one, but this one, C412CA, for example. Let me disassemble this so you can see. Yep, there's our shellcode. To convert that offset to a virtual address like this, we have to take that offset, which is this guy right here. We subtract the offset to the data seg section, the start of that section, which is this guy here, or pointer to raw data. That leaves us with what? Let me get my calculator back out here. We take let me get in hex, 4C0 ECA minus 4C0 C00. Oh, I messed that up. 4C0 ECA minus 4C0 CC0. We get 2CA. We want to add that to our section's virtual address, which is 84130. And then we want to add that to the image base, which is 4 followed by 5 zeros, 1, 2, 3, 4, 5, which gives us our final virtual address of C412CA, which in the patch version I have open here, not that one, but this one, is exactly where our shellcode ends up, right below that section of 32100. So that's what that function is all about, is just converting that offset to an actual virtual address. This is just getting the length of the hex string above, like getting the length of these kind of strings, because again, because I use that weird format, we have to make our own custom length function. So we take the hex string, we basically fill in the placeholders with spaces just to get rid of them because we don't want to count those as our length. And then we divide it by 2 because each of these bytes is 2 characters. And so we divide by 2. That gives us the length of these strings in bytes, basically. So if I passed this string to that hex, what was it called? Hex to, or length hex string, I will get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19, 20, 21 bytes, 21 as a length there. So we'll use that as a helper function. This is the replacement that turns the window in the patch version, which, do I have that pulled up still? I probably need to detach from it and close that. I think that's actually the original, yeah. Sorry, that sound's gonna play again. So in the patch version, it turns from Tycoon to Diecoon, and that was just taken from, I'm looking for this pattern of 3 null bytes followed by 3 null bytes because, let's see here. In here, or actually I'll look at it in IDA because I think it's you see it in the main entry point here. We can get the specific instance. So for example, before I get into that, let me go to the strings view here. Oh, there we go, subviews. I get confused switching back and forth. But if I go here and I type RollerCoaster Tycoon, there's a few places, or actually just 2 places that it shows up. I don't want this one because that's not the window title. I want this one. And the way we can tell this is the one we want, because if you look at the cross-reference here, it is used in the winMain function as the window name. That's how I kind of deduced that this was the right one to overwrite. And I just looked for the pattern of 3 null bytes followed by, oh wait, where is it? Not this one, but back here. Yeah, 3 null bytes followed by another 3 null bytes right after it. So I take that, and because Diecoon has one extra character than Tycoon, in order to make sure we don't overwrite anything, I use one less null byte in the replacement, you'll notice. All right, now this is the function that overwrites the actual data. So again, in memory, we're going to have all the data of rct.exe, the unpatched version. We're going to overwrite that data in memory using our new data that we're calculating on the fly here. To do that, because it's going to be a binary string and strings are immutable, we have to actually do a little bit of a Python trickery here. We're going to actually take self.data and reassign it to a join using whatever new data we're passing in. And this list operation you see here is just basically inserting or joining the data at whatever we're inserting. So basically, if I have, let me see how I can best represent this. Let's go to the hex view in IDA. Maybe that will help demonstrate. So if I'm just replacing these 4 bytes in my data from rct.exe, because I can't overwrite the data I already have in memory, I have to take, let's say I replace these with AABBCCDD. That AABBCCDD will be my new data. I'll do a join operation all the way to the offset I want to write to, which is going to be right here. I'll basically take all the data that comes before these 4 bytes, and I'll insert new data between that data and the data after those 4 bytes. That's basically what this is doing. And again, this is just a way to get around the fact that the Python strings are immutable, so we have to reassign self.data every time we make a change to the in-memory data. The patch function here just runs all these other helper functions to do all the patching in the right order. That's all these are doing here, so I'm going to skip over that one. This is patching the call instruction and replacing it with our patch call, which again, if you look up here, the replacement patch call, we take this guy, we look for this value, and then we replace it with this value, and that placeholder there is going to be the offset to our shellcode. So again, if I do a comparison between these 2 files, let me see if I can do that here. Yeah, right here. So we're taking this guy and we're turning it into this right here, these 2 instructions right here. And again, we leave a placeholder in there because we're going to dynamically calculate where the address to our shellcode will be. That's this guy right here. So the script will do that for us, and it will insert it in the right place, and then it will patch over that call instruction to make sure we call our shellcode instead. We then replace the explosion bitmap with the offset of the bitmap we want from our CSG1. So again, remember, excuse me, the bitmaps we pass in are going to have an offset that is an extra, that has an extra 0 on the end there, an extra place right here, numerical place right here. We really only want, so for example, if our offset is FA750 and CSG1I.dat, we really just want FA75 in the game. And so we shift that 4, which will drop off that 0. That's what we're doing right here. So we take the offset that the user passed in, which in this case I didn't pass one in, but by default it would be that B940. I don't know if I have, here, let me just run the help command. Yep, B94A0, excuse me. That's going to get shifted to the right by 4, which will just give us B94A, which will get written to this guy right here. See that reflected here. And what else? I think that's about it for this guy. Again, it just does some replacement work to make sure that the placeholder gets overwritten correctly. This just writes our output file, so the patch binary. Not much more to say about that. And this actually writes the shellcode. And again, I've added that +8 there to make sure we write it in the right region. This function also does all the MCI send string shifting in. So we take our path css25.dat, we put that into our MCI send string string here, and we put that right after our shellcode. After we calculate the address, we put those 2 strings for the open and the play commands to go right after the shellcode, And then we take the addresses for those two commands and put them into our replacement shellcode right, where is it? Here and here. Because remember, I don't know if I have that window pulled up still. Oh, I don't have the instructions there. But that's going to be our addresses to put into the MCI send string. It's going to be these values, right? I go to my patch binary here and here. So these two guys right down here. And remember, we do have to include these. If I put this into, hold on, let me take this guy for example, and I'll just do a quick CyberChef read of this. So from here, let's take out these and the placeholders. And from hex, yep. So remember, we're including quotes here because we need to make sure that if we have a path that has spaces in it, that gets escaped correctly. So the quotes are included in that code there. All right, so that writes the shell code, and that should be about it. The rest of this is just creating the horror patcher object itself, running the patch command, and reporting back if you're successful. Now, real quick, let's just do a quick example before we wrap this up. Let's say we don't want the skull to be used. Let's say we want a different bitmap to be used, and on my other screen here, I'm scrolling through trying to find something else to use. Let's say we want to use this, like, I don't know, this house for some reason. If we wanted to use this offset, what we would do is go to CSG1i and find where that offset in CSG1 ... appears. So remember, we have to do this in little endian, 1D, D4, 0C, 02. Make sure we do search direction all. That is this guy right here. And that is at offset F80D0. So if I wanted to update my Skelly bitmap or my explosion bitmap with something other than Skelly, I can just use that offset of F80D0. And oops, you know what? I forgot to take out my temporary, as I said, temporary logging info up here, right here. So let's do that before I forget and accidentally commit it. But that should mean that when I go to my patched version here and run this, instead of getting the skull now, when we do the Skelly test here, even though it's not a Skelly test anymore, when we get a crash, we should get a house now. And we do. We get that weird animation because I just chose a random house bitmap. Track stays the same. The horror track and everything else stays the same. We just updated the bitmap. And I won't show it here. Well, I guess we can show it real quick. We'll do a quick replacement of the selected track as well. And this time I'll use, here, hold on, let me see if I can scroll up here and just copy, this. I'll just use the 26 one that I also liked in that same folder. But you could set this to any WAV file you wanted to. So let's see if it plays the other track now when I crash the coaster. And it does. It's very faint, but you can hear it in the background. There it is. Kicks in a little bit once the organ starts. So there you go. That's our patch instruction. And with that, we are completely through the mod code. Congratulations for making it this far. And hopefully, even if you're maybe a beginner or intermediate with Python, you were able to kind of stick through and understand most of what's going on, if not all of it. If you do have questions, please let me know in the comments. Or if you have anything else that you see, because I have a lot of updates I need to make now. If you have anything else in here you see that's wrong, outright wrong, or if I missed something else which is completely, viable, let me know. I'm just taking a look through here to see all the changes I made to make this a little easier, and I think I'm happy with where this was. This is where the extra data was for some reason that I replaced, and make sure that we have our +8 there. Yeah, it's looking good. So I'll make sure to commit that in just a bit. Before we end the video though, I promised you an epilogue where I revisit the issue we're having, let's see if we can actually pull up the game and recreate it real quick, where we run the original game. And let's just load into the other save game I have. We go to options, we try to run to full screen. This happens. So this was the whole impetus behind the first RCT video, was I couldn't get full screen mode to work. So what we ended up doing is writing a mod to basically create, for lack of or in summary, to put it succinctly, we basically created a borderless full screen that worked and bypassed all of the weirdness that causes. So while I was learning so much about the RCT graphics, I started looking into this a little bit more. Hi again, it's Jeff from the future again. Yeah, the last couple of days I was feeling horrible and I had no time to finish this recording or edit anything. The whole rest of the video you just saw has been recorded for a couple of days now, but I've just had no energy at night to edit. So I apologize for that. I really wanted to get part 2 out well before now, like right after part 1, but here we are. Anyway, I'm feeling much better now. And again, in this last part of the video, I wanted to revisit the issue we saw in the first video. I don't have all the answers. I'm going to spoil that now. You're probably going to leave this section unsatisfied because I still don't fully understand the why, but I wanted to show you kind of what's going on now that I better understood the graphics and the system of the game, to show you what's going on with this error we see, or this glitch we see when we go to options here, we go to full screen mode, and all of a sudden we got this black screen until we resize the window again, and we're still in windowed mode. We didn't go into full screen mode. So I'm going to show you what I see and my hypothesizing I did while going through this video. But to be honest, by the time I got to this point in my research, I got well into the weeds of ddraw.dll. I just did not have the energy or willpower to go forward and really deep dive into this. If we wanted to, if you guys are really interested, we can do this in another video, but I'm putting this out there. Number one is a follow-up because I didn't really explain it well in the first video what the actual cause of this was. And number two, in case there's anyone out there who has better DirectX knowledge than me, who can maybe point us in the right direction or leave a comment on what they think is going on. So I'll show you what I see, and then I will leave you with that, and we'll call this one a video. So that was the exception I was trying to trigger all the other times that I talked about. I think it was in part 1 that you finally saw, but when I tried to do it in part 1, it actually didn't trigger. So this is why I had to attach instead of hitting restart. So we'll go ahead and do that. I'm going to, when we get in there, I'm going to set a breakpoint right here on this line. I'm kind of skipping a few bits because I want to show you exactly how I got here. So you may remember this jump table from our first RCT video. This has all the resolutions the game supports. So you see 600 by 800 here. You see the default 480 by 640 here. That's case 3. Case 1 and case 2, I believe, are for actually windowed mode. And then to the right here, you have all the other resolutions that are supported. This is the one that we're currently trying to select, which is 768 by 1024. In the first RCT video, you saw us like rewrite or patch over this part to make pretty much a borderless resolution full screen version here. So yeah, I'm going to set a breakpoint on this jump to show you what's going on when I change to full screen, which takes us here first, and why we're staying in windowed mode, first of all. So back in the debugger, let me go ahead. What was that address there for case 4? Or actually the jump, not the case 4. Here, go back to the debugger. Oh, I already said it. Perfect. So I must have done that right before I started recording here. All right, so let's go ahead and go back to the game. Oh, I'm so sorry if that's super loud because it's super loud in my ears. I'll obviously fix that in post for you guys. We're going to put it on pause for the rest of the time, so hopefully you won't need to hear anything else except for that small little sound there. So we'll go ahead and change it. And we're at that jump case, and you'll see we have the right value here, which is going to take us to case 4. Which, like I said, is indeed the full screen mode for, or I'm sorry, it actually is case 5 we're looking for, but the way the math works out, you'll see. it's going to end up in this case 5, and you're going to see it's going to go to the 768 by 1024 as we requested. So yeah, we get through this, but now watch. I'm going to hit, let's do this. Let's watch in IDA first. I'm going to show you, go down to case 5. There's a few checks that happen here. This one checks if a value on the stack is 0. If it is, it goes down to here, moves 0 into this memory address, moves that same value, I believe, right? Yep, same value into EAX and returns that. So let's see what what happens in our case when we get to that point. So that value in our case is right here on the stack, and it is 0 compared to 0 is obviously equal. So we do jump down there, we move 0 into that memory address, and most importantly, we move it into EAX, which is what's returned in the function that calls this kind of Windows resolution setting function. Let's go there right now. It is, let me go back up here, or actually I can just take it from the debugger. Take this address, go back to IDA here. So we are now right here, coming back from this call. So this is the call that pushed 5 to get us to case 5 in that jump switch here, in that last function. So now we're here. We're going to OR the last, the lower part of the EAX register, and if we don't, what do I want to say? If that value is 0, we're actually going to fall through to this next case and go to jump case 4, and you're going to see that. Let me go back to here. That's this guy, I believe, right here, 600 by 800. Yeah, FE29. Where even is that? Oh, it is case 4. It's right here, yeah. So yeah, so we fall through to this case 4, which is 600 by 800, but that's obviously not the one we requested. So something apparently failed. And when we go through this one, we're going to see the same result. We return with a 0, and we fall through one more time to the case where we go back to windowed mode. And then finally we come back here, and now when we jump, we're jumping to 0. So we failed all 3 of those other modes, whatever check is at the end of this function, and we're back at the default case, which is to windowed mode. I think I misspoke. I think I said that last one we saw right before I cut was windowed mode. That was the full screen mode for 640 by 480. Now this is the windowed mode. So what caused that failure that we saw in the first case that caused us to fall through all those cases? Well, let's go back. Let's go ahead and skip forward here. Now we see, well, first of all, the other thing is I'll show you exactly what's going on in the DIB. Now that we know how to check that, we'll go ahead and turn that breakpoint on for stretch DIB. Go to the DIB pointer, and not that, but follow dword and dump. And you see that we are all zeroed out except for very tiny spots where those pixels are colored in. So that's what's causing, that's the why, that's what's causing this issue. So I tried to dig at least a little deep and figure out what's going on here. So let's turn off this breakpoint and let's go ahead and try that again and try to trace through a little deeper this time. I'm going to go back, set this resolution. So let's go through here and let's see what's actually happening in this call to cause the failure that we see that returns the 0 and falls through all those cases. So let's go back to IDA here and we'll go to that function. So in 584AE2, I believe we might have seen this one in the first video as well. This does a bunch of what appear to be safety checks on kind of the resolution that was selected. And specifically, spoilers from my previous research, it is this line that causes us the mismatch and trouble here. So let's go look in the debugger at what happens when we reach there. So we move into EAX this value, which is our desired resolution of 780, which is 1920, or I'm sorry, that's not our desired resolution. That is actually the current high resolution of my monitor that I'm on right now. So that's what that is. And then let's see, we compare that. Here's the value I wanted to this value on the stack, which is our desired resolution. That's the one. Yep. That is, let me just double check my math. Yep, 1024. And then you see 768 below that. That's no problem. But when we get to this next part of the loop, and we go to the next part of this, it's indexing off this address here, you can see that this is the one that is still set to 640 by 480. And I believe it's this check that's causing this whole function to kind of fall out and return that 0 value. So what is this value here? Where does that come from? Well, if we set a breakpoint and write, and let's go ahead and run and skip over, I guess I can disable this breakpoint now. And we'll skip over that. And we're going to fall through it. Now, right here, that value was rewritten to, and that it's the same value, so you can't really tell. But that is at 5845 BE. So let's take a look there. Okay, so you can see that it's moving a value from AX in there. Where does that value come from? It comes from the stack. Well, what's interesting, you'll notice, is that this function and that value that's on the stack was not pushed from RCT, but from ddraw.dll, which is a DirectX library. Why is that interesting? Well, it means that DirectDraw received this function as some sort of callback, and so we're going to have to actually reverse into DirectDraw or ddraw to maybe figure out what's going on here. You also may have noticed, if you're paying very close attention, that DirectDraw is not anywhere in, or ddraw I should say, the imports for this RCT. Instead, if you look at the strings and search for DirectDraw or ddraw, you will find that it's dynamically located by RollerCoaster Tycoon by using load library, and then we can see all the functions being loaded via get process address. So if you were just looking in the imports list, you actually wouldn't even see ddraw there, but it is there. And like I said in part 1, this library is actually used to paint all the full screen, what I want to say, I guess, versions of our window. So whereas the stretch DI bits function is used for the windowed mode, there's some kind of code in DirectDraw that's used to paint the full screen mode. And I am absolutely a noob at DirectX and DirectDraw, so that's why I'm hoping maybe somebody else with more experience can kind of speak to what might be going on here. But all that to say that somewhere that library is setting the value, or at least it's calling this callback function, which is then setting the value in here from these values here. Let's see where these two values are coming from in the DirectDraw library by simply hitting go to return, and then we see that we return to an address in DirectDraw. However, this address is dynamically loaded, so what we can do instead to find where we are is load up DirectDraw into IDA, and then do a little search for any instruction here, and maybe hit or miss depending on how specific the instruction is. But here's the one I used. I already have it loaded up. Keep in mind this is the 32-bit version of DirectDraw, so we're in sysfile64 under Windows. We can search those opcodes, and we find only one match for this one in a function called enumerate mode, and that is right here. And this also receives those resolution values. You'll see them on the stack right here. So let's go one level up, and we end up in whatever this guy is at 580. So let's go back here. How many cross references do we have? Just a couple, and they're both in the same function, or actually there's more not shown. So let's do the same just to be certain where we know where we're at. Let's do the same technique of taking opcodes from here and searching them to make sure we get the nice, we get a nice sure feeling of where we are. So this is the one we want. So this is a function called, all the way up here, enum display modes. And I took a look at this function. I don't know if I still have the, let me go ahead and pull up the page. Essentially, what this function is meant to do is enumerate all the display modes supported by all the adapters, display adapters that are on your machine. That's how I understood it, at least. And so as it's going through this enum display modes function, if you look at right before we call that function that in turn called the RCT function, if we set a breakpoint right before that and see what's being moved on the stack, we can see that it's loading an address from right here, ESI-2, which is this region 8460 for FA. And that is also where we see some of these values like 258, which is 600. And I'm sure we see 480 loaded in there as well, if I remember too. If you look at, is it in this one? Yeah, 320, which was, how did I miss it? Is it down here? Yeah, there it is. I don't know. I must have been farther off than I thought. But yeah, you can see it right there. That's the resolution. And those are the ones that are passed into our RollerCoaster function and then compared. And that's why that check is failing. So where do those values come from in turn? Well, this is where I got stuck because it looks like it's drawing them from the hardware itself, that these are supported resolutions. It doesn't make much sense though why 640 by 480 keeps showing up. Because obviously my monitors are well above that resolution. So this is where I kind of got stuck because there's not much documentation out there that I could find on this function enumerate mode. And I tried to read more about the enum display settings and didn't get very far. Now, that being said, there's one other thing that I thought was interesting. If we go back to the debugger, that is back here. So I went back and I looked at where direct draw was being loaded dynamically into RCT and where they were getting the process addresses for all these functions. One thing I noticed that when you watch this and you get the process address, it actually returns an address in apphelp.dll, not an address in ddraw.dll directly. If you don't know what that kind of implies, apphelp.dll, and I'll try to find the page. There we go. It's an application compatibility library, and it uses what are called shims to kind of inject itself to, instead of making or letting a program load a old library and function calls directly, it kind of adds some additional layers of code to make sure things stay compatible with older binaries. You typically see it when you're running, for example, if I go to properties here, when you run this compatibility check and you check any of these, you typically have apphelp introducing shims to accommodate these. At least that's how I understand it. Someone please correct me if I'm wrong. This is it's been a while since I've actually looked at apphelp. However, you'll see that I don't have any compatibility settings on that I can choose, but it looks as if Windows 11 or Windows in general automatically adds some kind of how should I say, like auto shimming of older binaries here. So let's take this address, for example, for direct draw create, and let's set a breakpoint on that so that if that gets called, we can look. Or actually, I don't even have to call it. I just wanted to show you here that this is a hook into direct draw create, DWN 8 and 16-bit hook. So I'm not sure if this is related to the glitches that we saw, but I found it interesting that without setting any compatibility settings myself, apphelp is, adding these shims in. And maybe it's something that it always does with 32-bit binaries or older binaries. I'm not sure. And this is kind of where I hit the wall for what exactly is happening. It seems like what is happening is there's some kind of issue in the direct draw library where we try to use full screen. Some check goes back to the hardware, and for some reason, something's getting stuck on 640 by 480, and we're not passing those checks that RCT has internally, so it defaults back to the windowed mode. The other thing is I've seen countless reports of other people having flickering and black boxes and other things going on that all seem to come back to that direct draw library and playing older games on newer hardware. So again, I'm sorry to leave you wanting, but that's about as far as I got with what is causing this black box issue that we see here over and over again when we try to get into full screen mode. Anyway, I know that's not super exciting. I wish I had more to say on that issue, but I at least wanted to share that because I had a lot of people asking what exactly was causing the black box issue in the first place that led to that first video. And to be honest, I never even thought about looking after the root cause. I was just so focused on building that patch to get around it that, I didn't feel like taking the time to go back and study the graphics and everything to figure out what was going on. And today, unfortunately, I still don't know exactly what's going on, but I have a good idea it has something to do with compatibility between older binaries and that DirectDraw library. Again, if anyone out there is a DirectX guru and can kind of point us in the right direction, that'd be appreciated. But for now, I am ready to put this series in the books, and I am so tired. It's been a joy, don't get me wrong. But a lot of late nights researching, and now, this past week, a lot of late nights editing and recording. One more time, I just want to say thank you. All the late nights were worth it because all of you let me know how helpful some of these videos have been. If even a little bit, that's a win for me. And even beyond that, I see people sending me messages for how they, applied these techniques or this thought process to other things besides what we went over in the video, and did some amazing reversing and modding projects. So thank you so much for joining me for this one and part one, of course. And I really, really, truly hope that you got something valuable out of it. All right, it's late. I'm going to bed. Thanks for joining me. Have fun out there. Be safe. And as always, keep learning.